Okay, for the last part of giving us information for this chapter, we're going to start with our assumptions. So remember, once again, these are sort of the requirements you have to meet in order to do this type of test. If we can't meet them, there's other tests we would have to choose from. So we've got three, and we know the first two of them because it's the two we've always had and will continue to always have every single chapter. So the first assumption is for independent observations. This means what it's always meant, that taking one observation or set of observations, one measurement or set of measurements won't influence other measurements. The only thing is we've got an extra layer to think about here. So we don't want to corrupt our measurements within a sample or across samples. We don't want measuring one sample to influence the other sample. So we don't want measuring one person inside a sample to affect other people in that sample or people in the other sample. But it basically means the same thing it's always meant. Next up, and notice I pluralized this compared to other chapters, the populations we're sampling. Remember, we're sampling two separate populations. So each of those populations needs to be normally distributed. Again, our t-distribution from our t-tables is still roughly normal. So the populations we're going to compare them to need to be roughly normal in their shape as well. So population 1 and population 2 both need to be approximately normally distributed. Have that bell shape, right? The third one is something new for us. It's called homogeneity of variance. So remember when we're saying that something is homogeneous, or when things are homogeneous, that they have homogeneity, that we're saying that they are the same. So in our step 3, one of the big changes we had in this chapter was calculating pooled variance, taking the sample variances, the two sample variances, and combining them, pooling them. That's what pooling means. To combine things is to pool them, to bring them together. So we're going to pool them into one value. And so what this says for us is that our two variances, our two sample variances, need to be equivalent to each other. Now the book says equal, but that's misleading. You're never going to find two scores that are exactly the same. Equivalent, they need to be close together in value. So my variance for sample 1 and my variance for sample 2 need to be somewhat similar to each other. They need to be somewhat the same as each other, or it doesn't make any sense to combine them. If they're very, very different, they're probably really representing completely different sorts of distributions, which doesn't make any sense to combine. Think about it this way. If I asked for your age, and I got that number, how many years old you are, and then I got your weight, how many pounds you are, those are two completely unrelated distributions, right? Your age has nothing to do with your weight. But if I took your age and your weight and I averaged them, age plus your weight divided by 2, what have I calculated? That's right, nothing. I've calculated garbage. You can calculate that. You can take your age plus your weight divided by 2, but what's the number mean? Absolutely nothing. Those two distributions are so dissimilar, it doesn't make any sense to try to pool them or combine them. And that's the same idea here, that the two sample variances need to be similar. They need to be what we're going to say is equivalent as opposed to equal. That they need to be equivalent, or it doesn't make any more sense to combine them than it does to combine your height and your weight. So how similar is similar enough? There's a very formal way of determining that. It's another set of tables. Well, it's not a set of tables. It's another table and another calculation. It's called Hartley's F-max test. We're not going to be that formal about it. I'm never going to give you a hypothesis test and say, surprise, the two samples were too dissimilar, you shouldn't have done any of this. Remember, I'm never going to ask you those kinds of trick sorts of questions, if you will. So we're going to go by with using what's called a heuristic or a rule of thumb. So how similar is similar enough? What we're going to say is that the two samples need to be within 3 to 4 times of each other. That if we know one sample variance, the other one could be 3 to 4 times greater or 3 to 4 times smaller, and those values are similar enough. That seems like a pretty wide spread, but remember we're dealing with squared values, so we tend to have increased distances. So for example, if we knew that the variance for the first sample, I'm just going to say was 40 points, well, what does the variance for the second sample need to be close enough? Let's just go with the maximum here, 4 times. So it could either be 4 times smaller, which 4 times smaller than 40 would be 10. Minus. Or it could be up to 4 times greater. So it could be up to 160. Again, squared values. That seems like a really wide range, but it's not as wide as it actually is if we were to square root everything. So that's what we mean. If we know what the value of one sample variance is, the other one could be up to 3 or 4 times smaller or up to 3 or 4 times bigger. If we were doing professional research, we wouldn't use this heuristic. We would do the formal test to make sure. If they were more dissimilar than this, if my first sample variance was 40 points and my other sample variance was, say, 200 points, I will have violated this assumption, which says I really shouldn't be doing an independent measures t-test. Again, I'd have to go to some other type of hypothesis test that isn't in this course to do. So those are our 3 assumptions for an independent measures t-test. So the last thing I want to do with you, which is exactly like we did in Chapter 9, again, I hope every time you're studying, one of the things you're studying are your mantras. Again, they're fundamental to success in this course. So, mean differences, the difference between sample mean 1 and sample mean 2. If mean differences go down, then our t-statistic value should go down. And if our t-statistic value goes down, our odds of rejecting the null hypothesis go down. So just again, if we're talking about our t-statistic going down, we're meaning closer to 0, down in the absolute value sense. Let's do sample size. If sample size goes, let's say down today. If sample size goes down, error goes up. And if error goes up, your t-statistic goes down, and if your t-statistic goes down, we are again less likely to reject the null hypothesis. And the last one, let's do variance, or variability. If our variability or variance goes down, then if our variance goes down, our error goes up. No, I said that backwards. I'm sorry. If our variance goes down, I messed myself up. If variance goes down, error goes down. Variance goes down, variability goes down, error goes down. And if error goes down, our t-statistic goes up. And if our t-statistic goes up, we are more likely to reject the null hypothesis. So there it is, everybody. That is our lecture for Chapter 10. So on deck for the following week will be our lecture for Chapter 11, which is called a repeated measures t-test. So let me just say something I said way back, depending on when you watched it, the Chapter 9 videos: single sample t-test, independent measures t-test, and next week, repeated measures t-test. When you are taking the exam, for exam 3, the very first question on a hypothesis test you're going to be asked is, which t-test are you supposed to be running? So make sure you keep track of that. It's pretty simple. If it's just one sample measured one time, well, that's your single sample. If it's 2 samples, each one measured once, then that's your independent measures. And we'll talk about what the third option is for the next chapter when we get to it. All right, everybody. Hope you're all doing well. Hope you're not going too stir crazy if you're locked down. And hope we can see each other live sometime fairly soon. Bye.